Welcome, class, to the lecture video on section 5.5. This lecture video will cover confidence intervals for the difference between two population proportions. We may be interested in estimating the difference in proportions for the two independent populations, Px and Py. Now let's suppose that Nx is the size of a sample from population 1 and Ny is the size of a sample from population 2. And to be clear, when we're saying we want to estimate the difference in proportions, that means we are trying to construct their confidence intervals. So if the following conditions hold true, that our Nx times Px is greater than 5, and our Nx times 1 minus Px is greater than 5, and our Ny Py is greater than 5, and our Ny times 1 minus Py are greater than 5, then we can construct a 100 times 1 minus alpha % confidence interval on Px and Py. And so those conditions, that's just saying for each of our two samples, we need to have at least each of our two populations, we need to have at least 5 successes and 5 failures. And those p hats, remember, that is the estimated parameter that we create based on our sample. So as we would like to construct our confidence interval on Px and Py, we will use the following formula of Px hat minus Py hat plus or minus z alpha over 2 times the square root of Px hat times 1 minus Px hat divided by Nx plus Py hat times 1 minus Py hat divided by Ny, where that Px hat is x divided by nx. Remember, x is our number of successes in sample 1, and Py hat equals y over ny, where y is our number of successes in sample 2. To use this formula, let's take a look at an example. So our example is going to deal with the flu vaccine. So let's estimate the difference in proportion of vaccinated adults who get the flu and the proportion of unvaccinated adults who get the flu. And we assume that we have independent random samples for each population. So our information for our vaccinated adults is that we have a sample size of 50. We had 18 individuals get the flu, which would imply that our proportion of x over n would equal 18 over 50, or 0.36. For our unvaccinated adults, we have a sample size of 100. Our success for y is at 48 for those who got the flu. And so our proportion of y will be y over m, which equals 48 over 100, or 0.48. Now, by checking our assumptions, we see that for all of our samples collected, we had at least 5 successes and 5 failures. So that checks out, meaning we can construct a 90% confidence interval on our Px and Py, our difference between our population parameters. So plugging into our formula, Px hat minus Py hat plus or minus z alpha over 2 times our standard error of Px minus Py, we have 0.36 minus 0.48 plus or minus 1.645. Remember, this 1.645 comes from the z table, times our standard error of the square of Px minus Py, which would be the square root of 0.36 times 1 minus 0.36 divided by 50 plus 0.48 times 1 minus 0.48 divided by 100. By simplifying, we will get that our 0.36 minus 0.48 is negative 0.12 plus or minus our 1.645 times the square root of 0.004608 plus 0.002496. Simplifying further, we will have negative 0.12 plus or minus 0.13865, giving us a final interval of negative 0.25865 to 0.01865. And to put this into a proper interpretation, we will say that with 90% confidence, we estimate that the proportion of vaccinated adults who get the flu is between 25.9% less and 1.9% more than the proportion of unvaccinated adults who get the flu. Remember that less is because we have a negative value, and the more because our second value is a positive. So some interpretations of that confidence interval. We can note that since 0 is inside the confidence interval, a difference in proportions equal to 0 is plausible. Effectively, the result of this experiment indicates that vaccination was not effective in reducing the chance of getting the flu. We should note that the flu vaccine is effective for elderly and the ill, but the flu vaccine's effective is questionable generally for healthy adults. So one little thing as we're talking about our 0 being inside the confidence interval, when we talk in a couple, well, probably next week actually, we're going to start talking about hypothesis testing. And with hypothesis testing, a lot of it would be just asking questions like, is getting the flu vaccine effective? And one way to do it is to construct a hypothesis test. The other way to do it would be to construct a confidence interval like we did so. And if our confidence interval includes 0, that would lead us to a conclusion that the flu vaccine was not effective. Or at least we can say not significantly effective. Okay, so to finish this up, there is one little funny thing about this is that some simulation studies do suggest that the 100 times 1 minus alpha % confidence interval on px minus py should be computed as follows, with px tilde minus py tilde plus or minus z alpha over 2 times the square root of px tilde times 1 minus px tilde over nx tilde plus py tilde times 1 minus py tilde divided by ny tilde, where nx tilde equals nx plus 2, px tilde equals x plus 1 divided by our n tilde x, our ny tilde equals ny plus 2, and our py tilde equals y plus 1 over ny tilde. This is not something that I'm going to be testing you on, but it is something that you should be aware of. If I'm asking you a proportion question, I will be expecting you to use this formula. Okay, so that is the end of section 5.5 notes. Now you just need to run off and do your homework. Have a good night, everybody.